From our previous example on slide 4, we had a statically determinate problem. Our three unknowns, RAY, RAX, and RBY, were able to be determined from our equilibrium equations. That is, we took the summation of forces in the x direction and set it equal to 0, the summation of forces in the y direction and set it equal to 0, and we took the summation of moments about point A and set it equal to 0. In doing such, we were able to solve for our unknowns. But what happens in a situation where we have too many reactionary supports? For instance, if we replaced the roller at point B with another pin, we would introduce another reactionary force, RBX. In doing such, we would have 4 unknowns and only 3 equilibrium equations. That is to say, RAX and RBX are going to be statically indeterminate. We cannot determine these from our equilibrium equations. Now let us consider a situation where we replace the pin supports at A and B with rollers. We would have a partially constrained system. That is to say, we only have RAY and RBY existing at points A and B respectively. We have no reactionary forces in the x direction. That is, we have fewer unknown reactionary forces than equilibrium equations, and this means one equilibrium equation will not be satisfied. Additionally, we can have motion. Due to the application of P, Q, and S, we see that our body wants to translate to the left. There is no reactionary force to prevent this translation, and thus we could have motion. Now, let's consider a situation where we place 3 roller supports. That is, we have a roller support at A, B, and we create a new point E. To overcome a partially constrained system, we wanted to add one more reactionary force. In doing this, we see we have 3 unknowns, RAY, RBY, and REY. That is, we have 3 unknowns and 3 equilibrium equations, and we'd assume that we could solve for RAY, REY, and RBY. However, if we look closely, P, Q, and S all have x components, and once again, we do not have any reactionary force in the x direction, which means our body will have a tendency to translate to the left. The only way our equilibrium equation can be satisfied, that is the summation of forces in the x direction being equal to 0, is Px, Qx, and Sx have to be equal to 0, which by this diagram is shown not to be true. Thus, an improperly constrained system is where we have the proper number of equilibrium equations and the same number of unknowns. However, our system becomes statically indeterminate and we can have motion. To classify these situations of improper, partial, and redundant constraints, we will look at the following. A rigid body is improperly constrained whenever the supports, even though they may provide a sufficient number of reactions, are arranged in a manner such that the reactions must be either parallel or concurrent. This reflects a situation of where we had 3 rollers at points A, B, and E. That is to say, although there are the necessary number of equilibrium equations and the proper number of unknowns, these unknown reactionary forces are not sufficient to guarantee restraint. That is, our problem may be statically indeterminate or equilibrium cannot be satisfied, i.e., our body wants to move. The prescription of our additional support at E is not required to maintain equilibrium of the body, and thus it would be a redundant support. E could be removed from our system. Now, for a body to be completely restrained and for our reactionary supports to be statically determinate, we have to have an equal number of equilibrium equations as there are unknown reactionary forces. We call this a necessary condition. A necessary condition does not guarantee that our body will not move. The application of these reactionary forces guarantee that the body is restrained. That is, it's not partially or improperly restrained. And our reactionary forces are statically determinate. This is a sufficient condition. This would reflect a pin at A and a roller at B.